Hello and welcome back, everybody. Today we will look at the last part of 11.6, which is actually going to be on the very last test that we have to test for convergence or divergence for a series. So this last test right here is what is known as the root test. Now, the root test right here, I'll just tell you in advance that it is not necessary to know this one for the AP test, but just like the shell method, when it comes to the volumes of solids, it's just nice to have in your artillery because it's really easy to use, when the time comes, because, sometimes you just want to use the ratio test and it just doesn't work out. So that's what the root test is for. So here we go. Let me go ahead and introduce it then. So the root test basically says the following. If you take your equation inside the sequence, and let's say that you take the nth root of it, okay? Let's say you take the nth root of it, and it turns out that the limit as n approaches towards infinity of the nth root of the absolute value of the term is going to be less than 1. So again, you're looking at each term individually, and you're going to take the nth root. And if that term is going to be less than 1, the absolute value of it, basically just kind of like the ratio test here, then the conclusion is that the summation of a of n is going to converge absolutely, and then therefore it's going to be convergent. So note how the way that you solve for this is very similar to that of the geometric series test, right? You're basically looking at each term individually as a ratio. And then if you take the nth root of it and it turns out to be less than 1, then you're pretty much good to go. And similarly, just like kind of like the ratio test and the geometric series test, if that ratio is going to be greater than 1, or if it's equal to infinity, then that means that the summation of the sequence, or you can say the series of a of n, is going to diverge. And lastly, just like the ratio test, if you take the nth root of each term individually, the absolute value of it, and it's equal to 1, then there is going to be no conclusion according to this test. It doesn't necessarily mean that it converges, nor does it diverges. It just means that you probably have to use a different test then. So the question is, well, when do you use this root test? Because, now that we've introduced it, where do we see a situation where the root test would come in handy? So the best way to explain it is, well, if your equation for the sequence is raised to some power of n, so that means n is going to be your exponent, and that's where you're going to use the root test. So here we go. Take a look at these couple of examples where the root test would actually come in handy. So in this first one, I want to find out, once again, if this is going to be convergent or divergent. Now, if we were to apply the ratio test, just to kind of show you how this works out, you're going to get the following. You're going to write the limit as n approaches towards infinity of the absolute value of, and I don't think the absolute value matters in this case, 2 multiplied by n plus 1 plus 3, and then we also have divided by 3 multiplied by n plus 1 plus 2, and then all of that is raised to the power of 3 times n plus 1. That is going to be the next term. And then we're going to divide that by the current term, which is 2n plus 3 divided by 3n plus 2. And then we're going to take the absolute value of the whole thing. So this is what it looks like by the ratio test. And needless to say, this is not exactly something that's nice to deal with because you're going to have a lot of cleaning up to do. So you can see how the ratio test actually is not ideal in this case, and is probably going to fail in this situation. Nor is this something that you can use the other test for. It's not like it's easy to integrate this or to use an alternating series test or geometric series test and all that other stuff. So this is definitely something that the root test comes in handy. So let me show you then how the root test works out. So it says, first of all, I need to take a look at the nth term. So the nth term is basically this guy right here. I am going to take the nth root of it. So that means the nth root of that term. So nth root of 2n plus 3 divided by 3n plus 2 raised to the 3n. So limit as n approaches towards infinity, and technically absolute value of that. Well, the nth root, if I'm taking the nth root of something, that is the same thing as saying that something raised to the power of 1 over n. So what that means is that the n that you have in the exponent and the nth root right there, they literally cancel each other out. What you're left with now is limit as n approaches towards infinity of just the inside, 2n plus 3 divided by 3n plus 2, and then raised to the third power. Okay, and at this point, this is definitely something that you can solve for the limit. as n approaches towards infinity, you can just go ahead and apply it to the inside. So limit as, actually, here, let me just kind of write it like this so you can kind of see a little bit better. Limit as n approaches towards infinity of 2n plus 3 divided by 3n plus 2, and then that whole thing raised to the third power. Now for the inside, since it's both linear in numerator and a denominator, so that means that we just go to the coefficient, which gives us then 2 over 3, and then raised to the power of third, which is going to be equal to 4 over 9, which is less than 1. So therefore, by the nth root test, and I think people just really just call it the root test in this case. The summation of this thing right here, 2n plus 3 divided by 3n plus 2 raised to the 3nth power, it's going to converge then. Okay, and there you go. And that's going to be how you use the nth root test then. So let's take a look at this last example over here. This is relatively short for the most part. I want to again try to use the nth root test in this case to show that this is going to be convergent or divergent. So once again, this is definitely not something that we can use the other test for. Ratio test is probably going to be out of the question because it just looks so nasty, and it just doesn't fall into the other category. So what I'm going to do is now, once again, take the limit as n approaches towards the infinity of the nth root of that inside equation then. So 1 plus 1 over n raised to the power of n squared. And if you need to, just like I did earlier, I'm going to go ahead and rewrite this, so then that way you can see that the exponent is really just, once again, 1 over n. So 1 plus 1 over n raised to the power of n squared, and then multiply by 1 over n, because remember, you're taking the nth root of this. And fortunately, in this case, the n squared and then divide by n, that kind of cleans up nicely. So you're left with limit as n approaches towards infinity of 1 plus 1 over n raised to the nth power. And that guy you should definitely memorize by now is equal to e, which is greater than 1. So therefore, by the root test, the series diverges. And you can say it's because e is greater than 1 in this case. Okay? And there you go. That's what you do. All right, thank you so much for watching. I'll talk to you later. Bye-bye.